This video is going to be about graphs of simple harmonic motion. We're going to start out by talking about a displacement time graph. We're going to have time on our x-axis and displacement on our y-axis. And we're going to use a pendulum as an example. I'm going to start out with the pendulum in the equilibrium position. So this is a pendulum, it's hanging straight down. My pendulum's at the equilibrium position. My initial displacement for my pendulum is going to be 0. If my pendulum swings forward, it's going to have a positive displacement, so I'm going to draw my next point above the x-axis. After my pendulum swings all the way to the right, it'll have its maximum displacement, and it'll return back to the position it was at before, the equilibrium position, at which point it had no displacement. After it reaches the equilibrium position, it's going to swing backward. At this point, it's going to have a negative displacement, and then it's going to swing forward, complete its oscillation, and at this point it will have returned to the equilibrium position again. So, if I were to connect all these dots, I get my displacement time graph for my pendulum starting at the equilibrium position. We can see a few things from this graph. So if I were to continue out this trend, we see that this is a sine wave. So all graphs of simple harmonic motion are going to be either sine waves or cosine waves. In this case, the pendulum started with no displacement, so my wave is going to be a sine wave. If I started with an initial displacement to the right, so it had a positive displacement, it would be a cosine wave because I'd start out with some initial displacement. If I started out with my displacement to the left, I would have a negative cosine wave because I'd start out below the x-axis. We can see a few things when we look at a displacement time graph of simple harmonic motion. We can find the displacement, or the maximum displacement, or the amplitude from looking at each of the peaks that we have and finding the distance from the peak to the x-axis. That's my amplitude. If I wanted to find the period of the oscillation, how long it takes to complete one cycle, I could do it a few ways. I could measure peak to peak. So if I measure this peak here, this distance here would be my period. So if we clear away all the extra labels and things, we're just left with our displacement time graph. We can use this graph to draw the next graph we want to draw, which is our velocity time graph. Now if we remember from our mechanics unit, a displacement time graph's slope tells us the velocity of the object at that instantaneous time. So if we look at the slope when our displacement time graph in this case is 0, our time is 0, we look at this slope, we see that we have a very large slope at time 0, and then if we come out to this point here, we have no slope, so we have a flat line for our tangent, and if we just carry this on, next time when we come over here, our slope becomes negative. We once again have no slope. Slope becomes very steep again and it's positive, and no slope, and once again negative slope. Okay, so if we graph this out, so we start out with our time 0, so we have a high velocity initially. We go to no velocity when our slope is 0. We have no velocity, or we have negative velocity when our slope is negative. We return to 0, no slope. We have a positive velocity, we have no slope again, and then we return to having a negative slope. We connect all our dots, and in this case we can see that since we had a sine graph up here, the function for the velocity graph is going to be a cosine graph. And this makes sense if you know your calculus, because the derivative of sine is cosine. And we took the slope at every point of our displacement time graph to find our velocity time graph. It's important to note that the amplitude of our velocity time graph, this line here, tells us the maximum velocity. And the other thing we can see from comparing our displacement time graph to our velocity time graph is when our displacement is 0, our velocity is at maximum. And when our displacement is maximum, our velocity is at 0. Okay? So the last graph we have to talk about is the acceleration time graph. And we could arrive at our acceleration time graph one of two ways. So we could find the derivative of the points on our velocity time graph. So remember from our mechanics unit that the slope of on a velocity time graph at any point is the acceleration at that moment. But I'm going to go about it a different way. What I'm going to do is I'm going to use the definition of simple harmonic motion, which we started earlier. We said that we discussed in the earlier videos. So we said that acceleration is proportional to negative displacement. Okay? So this is going to tell us how we can draw our graph. So whatever the displacement is, this equation tells me that the acceleration is going to be opposite and proportional. Okay? So that means when my displacement is 0, that also means my acceleration is 0. If two things are proportional and one's 0, the other has to be 0. When my displacement is at maximum, I know my acceleration has to be at its most negative, its farthest down. And when my when my displacement returns to 0, my acceleration also returns to 0. And when my displacement is at its most negative, my acceleration's at its most positive. And when my displacement returns to 0, my acceleration returns to 0. And then when my displacement is at its most positive, my acceleration's at its most negative. And so we continue this trend on, connect all my dots. Okay, so we see that the displacement time graph and the acceleration time graph are opposites of each other. So if my displacement time graph, we already said, was a sine function, then my acceleration time graph is going to be a negative sine function. Some things worth noting are that when my acceleration time graph peaks, so the amplitude here, is my maximum acceleration. The other thing worth noting is that when my displacement is at maximum, my acceleration's also at its maximum in magnitude, but opposite in direction. Okay?